Ready? So today we're going to do this problem, and I have noticed that this is the kind of problem that people have said on different forums. It's kind of hard to explain. You can do it, but like when you're arguing it and explaining it, and I've seen like a bunch of YouTubers also saying that this is something that's hard. So I'm gonna try to explain this. So this is just going to be a study session, and I'm trying to explain this. We're gonna do perhaps this thing multiple times until this gets easier. So I know this is one of those perhaps crackhead problems, and so yeah, then it makes sense to put extra effort for this one. Okay, so let's look at the problem. Given an array of integers and integer targets, our input is an array and a target. Find a subarray that sums up to target and return the start and end indices of the subarray. Okay, so this is simple. Let's write it down on the paper. Okay, so we have one, 20, and then minus 3, 5, 4 is the array that we have, and then okay, this will write this. So one moment. Okay, so here we stop writing for some reason. Anyways, so these are our inputs. Now we have this on the paper. That's good. Okay, now gotta see how to approach this problem. And of course, you are the gist of this is you are going to have to provide a subarray. Now that subarray can start here and end here at this index, right? Or it can be something like this, right? Start at the beginning and end somewhere in the middle. Or it can be something like that, starts in the middle and ends in the middle, or this can go all the way to the end. So these are the cases, right? Now this is the kind of problem that we can solve with the prefix sum approach. So what do we have in the prefix sum approach? Now let's talk about that. As you know, in the prefix sum approach, we have the cumulative sum up to each index, which means, let me explain with an example. If we have this, then the cumulative sum for this thing would be, well, we don't have to do that really. Okay, so the cumulative sum up to this point would be 1. Then the cumulative sum up to this point would be sum of all the numbers starting from 0 to this point. That would be 3, right? And then the cumulative sum up to this point would be 3 plus 3, 6. Then here would be 10, and then 15, right? Now once we have, this is the property of the prefix sum. Then once we have the prefix sum, we can use that to get the sum of subarray. Now, if our subarray happens to be in the beginning, right here somewhere, right? Then we can simply get the sum from, if the subarray that we're looking for occurs at the beginning, then we can simply get the prefix sum and compare that with the target that is given. If the prefix sum that we have is equal to the target, then that would mean that our subarray is right at the beginning. At least the starting point is at the beginning and the ending point is somewhere, in the array, rest of array. But the point is, for this is an edge case which is easier to handle, right? So we could say, like, I'm not gonna go into writing the solution at this point, but the gist that I have conveyed, I'm sure you got that. Now, the other scenario is that we can be somewhere in the beginning, right? In the middle, right? So it can be like we can have be here, right? And let's call this one I and this one J, right? Now, how do we get I and J, right? Now, you do understand that at this point we do have the value for or sum of all numbers up to J, right? So that is an important detail. We do have that, right? And then you do know that we have 0 to I as well. And if you only look at this one, this value that we have, you can see that if we wanted to get I and J out of it, we are overcounting here, right? And we are counting by this much. So we need to take out this part, right? So if we subtract I minus 1, then that would give us ij. So now why am I subtracting I minus 1? Because if I subtract I itself, then I is going to be part of the chunk that I'm ignoring. But I want it to be the part of the chunk that I'm focusing on. That's why I need to ignore all the values that are before I. And what is the value that is right before I? That is I minus 1. So that is why I am doing I minus 1. So hope that part makes sense to you. Okay, so having said that, now we are here with an equation. Now, how can we make use of this equation? I have seen at this point people suggest, okay, this looks like to some question. This is what people suggest. I want to go that route because underneath this equation, underneath the equation, the two sum question have, right? So there is an underlying technique, so people don't really peel off those layers, right? So in this question they would be referring to the two sum question, and what that would mean is the person who's listening would have to know about the other question. But I don't think this is like the first principle kind of thinking. So maybe we should peel all the layers off of two sum and get back to get to the bare bones, and then reason from that, right? That's what way want to do, right? So instead of invoking two sum, I would go to the two sum and try to peel all the layers and see where we can the point we can get to, right? So let's do that. Okay. Okay, so I have opened the do some question in front of me, and I'm gonna write down its answer. I mean the question on the board, and then we're gonna peel the layers because most people are able to solve it, but they stay at the superficial level. So I think I wanna go a step deeper than that, because in the process the knowledge that you get, then you can apply it anywhere. So you have 2, 7, 11, 15, and then you have to come up with two numbers whose sum would be equal to 9. Now the idea is that those numbers can be anywhere. This is important and we need to pay attention to that. So if we were going to find these two numbers, now these can be anywhere. So whenever two numbers can be anywhere, right? Then let's call that scenario that those two are fluid value while this one is a fixed value, and these are fluid value. So since these can be anywhere, it's going to be more expensive to look for the right pair by trying all the pair, because this is mostly what is done in the brute force solution. You have one loop that is tracking one number, and then you have the other loop and that is tracking other number, right? And you have some conditions here, and then you're trying all the pairs. But the problem with this approach is that you're trying all the pairs, and when you approach this equation in this form, your idea is that, okay, I'm gonna try. When you have it written like this, you might think, okay, I'm gonna try all the pairs and see out of those which one is equal to the target, right? But there's a better approach to do this, right? And we come to realize that once we rewrite it, and this is so once we rewrite it like this, now what do we have? Well, we have one fixed value. That's good thing, because this is something that we know. We don't have to look for, right? In a search space, right? This search space that we have. The problem with this approach is that this is a search space that is well, flexible, so the number can be here, 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 anywhere, right? So that's why we have to try a bunch of mm, um, bunch of combinations. But here, what do we have? We have a fixed value, so this is something that we don't have to guess, right? And then we have y. Now y is something that we have to guess, let's say, or we have to try all the combinations. But the benefit of y here is that we can do this in a single pass. Why? Because if, let's say, we have a single loop, that's gonna cost O of n as opposed to O of n square, right? So we can say that the loop, a single loop, will control, will scan through the array, and it will substitute those values in place of y, right? And the idea is that this way there is only one fluid value, the other one is fixed. Now this is going to give us a value that, if we have that, then this equation will be satisfied. And when this equation is satisfied, then what does that mean? That means we have come across two numbers that satisfy the target equal to 9 condition. So instead of, the idea here is that instead of looking for two numbers directly, we are doing it in a rather convoluted way, or we're saying, okay, what is the number that should be there to make sure the target equal to 9 is the value. Now this equation tells us other things as well, so let's try to think of those. So the moment we calculate this, now we need to know, we will get a value of x. Now we will need to know whether this is the value that we have seen. If this is the value that we have seen already, let's say we were going through the array, right, and we come across a value target, well, we have a y, and then we calculate the target y, And if this is something we have already seen, now how do we keep track of something we seen? That's where the map comes in. We have the map. So in the all the values that we have seen, so as we'll go through the array, we'll keep track of all the value that we have seen. And so let's say 1 2 3 4, and we keep marking those. And when we find we get this, we'll check whether this is something that exists in the map. If it does, then that means we have already seen it, and we have already seen it. Then that means we can say that we have come across values that satisfies this equation. And if we have come across values that satisfy this equation, what does that mean? That means we have also this equation was based on the question, right? And this was the original form that stated that if we have found something, this also means that for these x and y numbers, the target condition will be satisfied. Now, this is the point that I find kind of hard to argue, but I think my explanation is getting better. So that's what I'm trying to stick to. Okay, so let's give it a one more try. The idea is that you're going through the array, and you are you're going through the array, and the loop variable represents, so you're iterating through the array, and the loop variable represents uh, the loop variable represents, of course, the number that we are currently looking at, right? And that's where we can do, we can subtract it out of target to see if target minus this number is something that we have already seen. But why would we do that? Because when we do that, we would come up with a number, let's say y, and that y, if we have seen that y, then that would mean we have come across a y which would satisfy this equation, yeah. I guess that's one way to put it. So let's try this one more time, because this is something I think. No, let's not one more time. We need to do it again and again. So let's say you're going through the array, because I want to be able to explain this verbally. I think one of those things, this is complicated, or like other things are complicated, but you have to be able to explain it a little bit, and maybe perhaps with the requisite amount of preparation or practice, you can do that. Not preparation, I mean practice itself is the preparation. So I would not go as far as calling for the preparation, because the problem with that approach is, let's say you prepared for x, and you get like a different variant, then it's going to be problematic, right? So there is that. Excuse me. Okay, so let's say you're going through the array. So, I mean, one way to find the value that we're looking for. Right, let's say, let's talk about the question. Okay, so we are given an array, and we have to find two numbers that sum up to k, or the sum up to target, right? Now, there is one way to solve it where we generate all the pairs. Now, this is an expensive proposition because it's going to cost n square. And why is this going to cost n square? Well, I can do the analysis of the piece of the paper, but the idea is that if you have this array, right? So you'll the first subarray would look like start and end here, and then here, here. These are all going to be the sizes of the subarray, right? So these are all the subarray that start at index 0, right? And then we're gonna have to repeat the process. So notice something. How many subarrays we create? One, two, three, four, five, six, six. And how many items we have? Size of n is 6, right? So what does that tell us? Well, that tells us that for a 6, I mean, in terms of n, we can say for the first index, for the all the subarrays starting at the first index would have n subarrays. Then here, how many subarrays we would have? We'll have n minus 1, and then n minus 2. How many subarrays we will generate at the very end? Well, we'll generate 1, because when we're here, this is the only subarray that we can generate. It starts at 6 and ends there. Hmm. And what will be the sum of this? Because this is an arithmetic. Series, right? And some can be found this way. So let's try to find that. A represents the first term, so it's going to be n. And then we have, how many terms do we have? Well, can we say we have n terms? So we start with 1 and we go all the way to n. Yeah, I can say this is because we have n terms, and then these minus 1. So let's solve this one. 2n minus n plus 1. So this would leave us with n plus 1. But this is just going to be open square, ignoring the less dominant terms and the constants, right? So this way, if we are going to generate all the subarray, the cost would be n square, and we don't really want to do that. That's why the optimization is that if you have an array, if you have an array, instead of looking for pairs directly, right, looking for these pairs directly, you look and see that these amount to certain target. That's one way to look at it. But even better is that you get the target and subtract y from that, and that would give you a value, a potential x. Now, why do I call it potential x? Because if this thing is something we have already seen, right, That means currently we're looking at a number y, and then we have a value of x that we have seen. That means currently we have come across a pair. Now, what is the benefit of this approach? Well, the benefit is that we won't have to do n square, right? We can just do, okay. But what if they said, well, I was just going to go in a hypothetical question, but I think we can leave that for now. Let me just make a note about this and I can explore that. The question that I was thinking of was that what if we are asked to come up all such pairs where, or rather the count of all such pairs where the target is equal to, so as I was saying that there is a slightly different question that can be asked, and that question can be asked to come up with the count of all such pairs where their sum is equal to target, right? So that can be an interesting problem. I'm going to do that later, but yeah, this is an interesting problem to think about. And then also I gotta think about why are we just using the prefix sum? Why not the try sliding window? So that's another one. But this is this informal study session, and idea is that it kind of works like perhaps the Pomodoro, you know. Okay, let's try to argue or explain this to some problem. So we're given an array and we have to come up with two integers and their indices rather that sum up to target. Okay, that tells me that we have to find, well, I think here is the trap. Well, we think we have the liberty to write at the tail, the board, because when we take that liberty too early, we are perhaps only good at the explanation that we can solve on the piece of paper. But oftentimes you have to explain those things verbally, right? How would you do that if you haven't tried explaining things verbally, right? So, yeah, maybe to some extent we should do that. You know, Euler perhaps used to do that. I suppose he used to. I think I've heard somewhere he used to. Anyhow, so let me just imagine it. So we have this array, and then we have the target, and now we have to find two numbers that sum up to that target. Hmm. So for something like this, there are two ways. The first is the brute force. In the brute force, you can try to you look at that array, and that array tells you. That equation tells you that you have x and y. So you have to try all the x and y pairs and come up to a target and see which of those would sum up to target. But then, as you can perhaps see, this is a bad approach because that we are trying all the pairs. So, is there a way we can change it and we can avoid looking for all the pairs? That is the important question we need to think about. Like that's the way we need to approach it. say that the perhaps the people have hard time with delivery because they're able to argue this, but then they're not able to argue this verbally like what they're doing over here. If they could do that, then the things perhaps would get easier for them, because it's like the verbal aspect that is holding them back, you know. So basically I'm going to try to explain this. Hey, so I'm back and let's try to explain the two-sum problem again, and this time without using any visual aid or anything like that, because I'm thinking of developing the verbal explanation skill as well, because this is like most important thing perhaps. Anyways, so what about the problem? Well, what is the problem? The problem that we're given is it's an array of integers, and then we're given a target. Now we have to find two integers that sum up to this target number. So basically, we talked about the brute force approach and we know that is not feasible, right? So but what is it that we can do better? So for every number in that array, right, the number that we're looking for, so let's say for every number in that array is x, the number that we're looking for is target minus x, right? So that is the number that we're looking for. Now what I did in this explanation, I tried to sidestep the justification part. I just gave you the gist, right? So I think that is the way we need to approach it. We just need to give the gist first, and the justification, those kind of things, that can be done on the whiteboard or verbally as well. But then we can talk about that in detail, right? Now then, at that point the other guy would also have the expectation that that's how we're gonna go, right? But instead of that, you build this cognitive load when you try to explain everything in the beginning, right? So I think I noticed that the neat code guy does that, so I'm trying to do the same, which is to reduce the cognitive load when you're speaking, right? I think the fluid communication happens when you have the reduced cognitive load. But when these complex constructs basically take up all your mind space, then you don't have anything, you don't have the room to do the explanation. Perhaps that is what is going on. Anyways, so I'll get back to it, but yeah, for now I think this should be good enough.